In earlier videos, we saw that this proposition was true when the domain was the odd positive integers. This proposition is also true for the even positive integers. 2, 4, 6, 8, 10, and so on. If you add two evens, you get an even. But this proposition is false when the domain is all of the integers. And it's not the fact that the integers also have negatives. This proposition is true when you have negative, when the domain is positive and negative odd integers. And this proposition is also true when you have positive and negative even integers as your domain. The issue lies when your domain is all integers, that this is for all x and for all y. For all x and for all y. So it's saying that no matter which x you pick and no matter which y you pick, when you add them, you're going to get an even number. And that's just simply not true. Right? Think about 2 is an integer. 3 is an integer, but when you add them, you get 5. 5 is not even. So in this case, you see that the domain is really important. By choosing one domain, you can get a proposition. So you can use if you use the same proposition, choosing a different domain, it may make it true or false. Okay, so in this case, we see that the proposition is false. Now, in part C, you're supposed to also provide a counterexample. We've already found that one of many, there are infinitely many counterexamples above. 2 plus 3 equals 5 is a perfectly good counterexample. So you could put that here. 2 plus 3 equals 5. Now there's one more thing that I should say about this. Okay, now I want to show you how you might want to go about this if you couldn't just tell that it was false. Okay, so what you would want to do is, first of all, just say to yourself, okay, let's look at some examples. All right, so let's assume that the prior discussion of this video hasn't happened and that you're approaching this problem for the first time. And let's just assume that you've never seen this proposition before, never seen any proof of it before. What you might do, just to start, is you might say, okay, let's pick some examples. All right, let's pick two even integers. Okay, let's see, 2 plus 10 is 12. That's even. Okay, so it's true there. All right, let's pick two odds. 3 plus 11 That's 14. Okay, it's true there. It's true for, so here we see that it's true if you have two evens. If you have two evens, and you add them, you get an even. If you have two odds and you add them, you get an even. So what about, let's see, is there any cases that I'm not taking into account? Now, let's see, this is saying all possible integers x, all possible integers y. Aha, what if I add an odd and an even, or an even and an odd? What happens then? So you might say 5 plus 12, that's odd. That's not even. So an odd plus an even is an odd. And here's your counterexample. Yet another counterexample. Okay, one last thing to say about this. Now the proof here, there's nothing, this proof is not, you can't prove a false statement, okay? You can't prove a false proposition. So, but if you read through the proof, nothing in the proof is really incorrect. Let's see, the assumptions are stated. This part right here, it proves that if you add two evens, you get an even. Okay. This part right here, it proves that if you add two odds, you get an odd. And each of these parts, this part and this part, are perfect proofs of those individual facts. The individual fact here that even plus even, here even plus even is even, and here odd plus odd is even. But the problem is that this proof leaves out a big piece. And that's the piece that we found up here. That when you add an odd to an even, you get an odd. And similarly, it leaves out the case that when you add an even to an odd, you get an odd. And so there's a whole case that's being left out. The whole case being left out is odd plus even. Okay, now I don't mean to imply that what I have written here is some sort of proof. This is just shorthand to try and emphasize that a whole paragraph, a paragraph probably as long as one of these ones here, has been left out. And so it's possible to write a proof that doesn't have anything entirely wrong with it, except for the fact that a whole bunch of things that you should talk about have been left out. You can't create, or you can't come up with a correct proof of something that is false.